All right, AP Chemistry class. This is the solution video for the winter Christmas break take-home assignment. I'm going to do this in pieces so that I can get these up as quickly as possible. So I'll probably do 2 to 4 pages at a time and get these up over the course of Tuesday, December 24th and Wednesday, December 25th. Okay, so let's get started. There's a variety of problems. These are all review problems. Going all the way up to molecular orbital theory, and let's go ahead and do these. Okay, so the first one, we're going way back to the first week, significant figures. So you use PEMDAS, so you do multiplications and divisions first. And so what we are going to do is we're going to go ahead and multiply 3.24 times 5.3 divided by 2.45. It doesn't matter what order you do those in, and you'll get 7.00. We'll call it 9. We'll go to 4 significant figures because right away we can see we're not going to go past 2 significant figures. So this is a safe number to stop at. And we're going to just put a little 2 above that to indicate that we're at 2 significant figures here because there are only 2 significant figures in that number. All right, now what you're going to do is now you have just all of this added to this, subtracted to this. That just goes straight from left to right. So we're going to take this number, 7.009, and that should be plus, and it's going to be 6.7. Well, let's go ahead and do this the proper way. I'm sorry. It's 7.009, and it's going to be 6.782. And then it's going to be, well, let's go ahead and add that. We get 11. 8 and 1 is 9. 7 and 13. Now we're going to subtract 0.0325. By the way, when we cut this off, we cut it off right there because that's the least number of places after the decimal is 782. This was actually a number that went on much longer than that, but we're going to cut it off here anyway. So remember, with addition subtraction, you cut off at the least number of digits after the decimal place when you add or subtract. So we have that. Now we're going to go ahead and we're going to go ahead and cut this off right away. So 11 minus 2 is 9, 9, 8, 8 minus 3 is 5, 7, and 13 minus 0 is 13. And it's the same number of places after the decimal for each of these numbers. Well, this one was 4 and this one was 3, so we're going to cut it off at 3. And there we go. All right, so that gives us 5 significant figures right there. However, we noticed back here that we only had it to 2 significant figures, so that's going to be these 2 digits right here. So this first digit that is not a significant figure, you use to round this one. So that means the answer to this is going to be 14. Okay, and you can put a decimal if you want to indicate that that's absolutely that many significant figures, but do not put a 0 after the decimal, or that would indicate that that's also a significant figure, and there's only 2 significant figures. Okay, definition of an isotope. I'm going to speak the verbal answers, the ones that require a written word answer. I'm going to only speak those because I don't want you to just copy my words. I want you to put it in your own words. So an isotope are 2 atoms of the same element, but with different numbers of neutrons and therefore different atomic mass, and they will have a different mass number. So same element, but different mass, different number of neutrons. They both have the same number of protons. They have to, or they wouldn't be the same element. And if we're just talking electrically neutral, they have the same number of electrons. All right, draw a Bohr diagram of the following isotopes showing all protons, neutrons, and electrons. Well, I just gave you one to do. So if we do that, it is going to be, what this is this the atomic number? That's the number of protons. And this is the mass number. Atomic mass is the average of all. That's what you see on the periodic table. It's the average of all of the isotopes. This is a very specific isotope, and so this actually is a whole number. It has 14 protons and neutrons. I'll write that right here. Protons plus neutrons. Okay, so that means it's going to have 6 protons. You have to draw these in any particular location. Those are all protons. And it has 6 plus some number equals 14 number of neutrons, or 14 minus 6 number of neutrons, and that's going to be 8. So I'm just going to draw that like this. And those are going to have equal signs in them. Normally, when we were diagramming atoms way back at the beginning of the course, if we had more than a few, we didn't draw them all, but I wanted you to just draw them out. Okay, then you have the first orbital, and it has 2 electrons in it. And you have the second orbital, it's carbon, and we space these out just like we would on a Lewis dot structure. There's 1 on each side like that. And there you go. That would be the Bohr model for a carbon-14. That's the one. Let me get down here a little further. That's the one that's well known for determining the age of artifacts, ancient artifacts. Okay, what's an anion? An anion, so an anion, I'm just going to say this in words. An anion is 2 atoms of the same element, but with different numbers of electrons. And therefore, an anion specifically has 1 or 2 or more extra electrons. So an anion has more electrons, is the atom of an element that has more electrons than protons. And therefore, it has a negative charge to it. So go ahead and put that in your own words. Identify the charge on the following atoms when they become anions. Well, you get your periodic table, and if we look at oxygen, it needs 2 electrons to be like the nearest noble gas. That's neon, so it wants to add 2 negative charges. So oxygen's going to be a 2 minus, and chlorine needs 1 electron to be like the nearest noble gas, argon, so it's a 1 minus. Or you can just put minus. Okay, what is a cation? A cation is an atom of an element that has more protons than electrons, meaning that it's lost electrons. This would be characteristic of metals, of any of the metals. When they become ions, they become cations. That is to say, they lose electrons. So it has more protons than electrons because it's lost electrons. It can't lose protons or gain protons, but it can lose electrons. So that's a cation. Identify the charge on the following atoms when they become cations. So we do the same thing we just did, except over on this side, strontium. So strontium to become like the nearest noble gas. The nearest noble gas is not the one in its row, xenon. It's the one if it goes back 2 places to krypton, that would be it. So it wants to lose 2 electrons, so it could be like krypton. So strontium is 2 plus. And sodium up here wants to lose 1 electron, so it can be like neon in the second row. And so it's 1 plus. All right. Using the concept of Z effective and a numeric example, explain why fluorine has a smaller atomic radius than lithium. Okay. Well, as I said, I'm not gonna write the words out. I will speak them, but I will do the numeric example. So fluorine, Z effective, is the number of protons minus the number of core electrons. So I'm going to just draw a quick Bohr model of fluorine. The way we did it back at the beginning of class, it has protons, it has neutrons, and fluorine has 9 protons, and the typical fluorine has 10 neutrons. All right, so now it has 2 electrons right here in the first orbital, and then fluorine has 1, 2, 3, 4, 5, 6, 7 electrons in the second orbital, so 7 plus 2 is 9. So it has the same number of electrons as protons. We do the same thing for lithium. Lithium has 3 protons, and the typical lithium has, the most common isotope has 4 neutrons. We know that because 6.94 is the atomic mass. That's very close to 7. So we go ahead and put a 4 there. All right, then we also draw this, the first orbital, and this, the second orbital, which only has 1 electron in it for lithium. Okay, so the question is, using the concept of Z effective, and in numeric example, explain why fluorine has a smaller atomic radius. So fluorine has a lot more protons, neutrons, and electrons than lithium does, but why is it smaller? And the Z effective for fluorine, the Z effective is the number of protons, which is 9, minus the number of core electrons, which is 2. So that means all of the 7 electrons in the second orbital of fluorine feel as though they're being pulled on by 7 protons, because that's the Z effective for fluorine. For lithium, the Z effective is, it has 3 protons, it has 2 core electrons, those are the electrons inside of the valence orbital, so it has an effective charge of only 1. So this electron feels as though it's only being pulled on by 1 proton. Since these, even though there's a lot more electrons, since they feel like they're being pulled on by a lot more protons, and since they're effectively really not blocking each other out because they're all side by side, we know with our more advanced models of the atom that's not necessarily true, but it's still more or less true. They're all pretty much the same energy level out far away, that they get pulled in really hard, because effectively 7 protons are pulling on each one of these, whereas only 1 proton is pulling on this one. So that means that fluorine, even though it has more protons, electrons, and neutrons, is going to have a smaller atomic radius than will lithium. Okay, so this is a concept that we didn't talk about in class, but Ms. Caprell talked about it in the NIMSY workshop, and that is the concept of ionic radius. And it's very similar to atomic radius, except it deals with a little bit more with the Z effective of the atom. So if we look at it, we have S2 minus, we have argon, we have rubidium, well, I kind of botched this problem. I'm gonna make a change on this. What I meant to do was this. I meant to make this potassium 1 plus, and I meant to make this calcium 1 plus, or excuse me, 2 plus. And why I'm doing that, you'll see in just a second. Okay, so this should be potassium 1 plus, calcium 2 plus. Okay, and some of you will see why I did that. I did that because I want all of them to have the electron configuration of argon. So if you add 2 electrons, the sulfur, it becomes like argon. Of course, argon is like argon. If you take an electron away from potassium, it becomes like argon. If you take 1 away from this, it goes back to the next row back. That's argon. And if you take 2 away from calcium, that becomes like argon. So all of these have the electron configuration of argon. So which one would have the smallest and largest atomic radius? Well, the one that would have the smallest is the one, since they all have the same electron configuration, same number of electrons in the same orbitals, it would be the one that has the most protons. And that would be calcium. So calcium has the most protons pulling on the same number of electrons. So calcium is smallest because the protons are pulling the hardest on that same number of electrons. And the one that would have the fewest protons is sulfur, and it has the same number of electrons. So it doesn't have as many protons pulling on those electrons. So sulfur would be largest. All right, define ionization energy. Ionization energy is the amount of energy required to remove an electron from an atom in a gaseous state. Technically it's a gaseous state, but it's basically how much energy does it take to pull an electron away from an atom. We often talk about it as how much does an atom want to hang on to its electrons. If it's low ionization energy, it doesn't want to hang on, but it's technically how much outside energy is required to pull that electron away. Okay, define electronegativity and electron affinity. I just threw these together in the same question because we usually use the term electronegativity, but there's technically a difference. So electron affinity is how much an atom wants to pull an electron away from another atom, from outside of itself. So that's what we would actually have in an ionic bond, where a nonmetal with high electron affinity pulls electrons away from other atoms. Although we often refer to that, and even sometimes textbooks refer to that as electronegativity, technically it's electron affinity. What electronegativity is the similar concept. It's how much an atom wants to pull an electron away, but in a covalent bond. So it's not pulling the electron completely away, it's sharing the electron, but it's pulling on it. And higher electronegativity means it pulls on the atom or on the electrons of another atom to which it's covalently bonded. Harder, that would create a polar covalent bond if it has if there's an electronegativity difference between the two atoms. So again, listen to that explanation a second time. I want you to write it out in your own words. That's why I'm not writing it. So electron affinity is how much an atom wants to pull an electron in from the outside or from another atom. And electronegativity is how hard does it pull on the electrons that it shares with another atom in a covalent or sharing type of bond, a non-metal type of bond. Okay, briefly describe a covalent bond using the term share, electronegativity, octet rule, nonmetals, and optional two strong guys if you want to use that metaphor. All right, so covalent bonds are formed between nonmetals. Those are the gases, generally gases in the upper right-hand corner of the periodic table, not including the noble gases. So it's nonmetals. Those both have high electronegativities and high ionization energies. That means they're strong guys. They like to pull on the electrons of other atoms, and they don't like to give up their own electrons because they're strong. So when two strong guys get together, they have a tug of war for the electrons. Neither one can win, so they decide to share those electrons. If one guy's a little bit stronger than the other, say nitric oxide, where one is oxygen and one is nitrogen, then the oxygen's a little more electronegative, so it will pull the electrons a little bit more towards it, and that becomes a polar covalent bond. If you have an O2 molecule, an oxygen molecule, you have two twins basically having a tug of war. They're equally strong, so nobody pulls on the electrons more than one of them doesn't pull on the electrons any more than the other, and so that's a nonpolar covalent bond. They do it in such a way that they create an octet for themselves, and the shared electrons count as electrons for for each of the atoms that share them. So that's basically simply the definition of a covalent bond. Again, you can go back and review some of your early assignments for that. 13, briefly describe an ionic bond using terms low ionization energy, high electronegativity, pass, pull, non-metal, metal, optional weak guy, strong guy, cation, anion. Okay, so if you get a metal and a non-metal together, and the metal could be in the transition metals, but most often in the examples we used alkali and alkaline earth metals, the first two columns of the periodic table, because they have the lowest ionization energies. So you take a nonmetal with a high electronegativity or electron affinity to be more proper, that likes to pull in outside electrons, and you take a metal, alkali or alkaline earth metal with a low ionization energy, so it doesn't take much energy to pull its electrons away. And what will happen is the nonmetal will be able to completely pull an electron away from a metal. So the strong guys are the nonmetals, the weak guys are the metals. So you can say they pass or pull an electron. Electron gets passed over to the nonmetal from the metal. and that makes the nonmetal an anion because it has a negative charge. The metal becomes a cation because it's lost an electron, so it has one more proton than an electron, or maybe two, and so it's a positive charge. So that positively charged ion and the negatively charged ion attract each other. And generally, ionic bonds are considered to be those which have between two elements which have an electronegativity difference greater than 2. So if the electronegativity of one element is 2.5 and the electronegativity of another element is 0.3, if you subtract those two numbers, you get 2.2. So that would be a large enough electronegativity difference to create an ionic bond. Less than 2 would be some sort of a covalent bond, polar covalent or nonpolar covalent, depending on how much lower it is. All right, we're moving on. Compute the molar mass of the following. So that's a numeric problem. I'll go ahead and do that. So you get out your periodic table, and we just do this. We have 2 irons times 55.85. And we have 3 oxygens, and that's times 16. Okay, and that gives us 111.7. This gives us 48. You add those two together, and you get 159.7 grams per mole of Fe2O3. Okay, for C3H8, we have C. There's 3 times 12.01 equals 36.03, and H is 8 times 1.01, and you add those together and you get 45. Excuse me, 44. Maybe something was wrong with that. 44.11, and it's grams per mole. Or the way we wrote it traditionally in class. Let me get back on screen here. The way we've traditionally written that for this one is 1 mole C3H8 equals okay, so this spells it out more clearly. But this is the way you're often going to see it written. It's just 44.11 grams per mole. Okay, so now we're on to number 15. This is one of the tables we used early on in the course just to get a concept of how you put atoms together to create molecules, how you determined atomic mass, and then ultimately molar mass, which is what we work in. And then sometimes you do want to know the number of particles that you have that you're working with. So let's go ahead and fill this out. So in HNO3, number of atoms or molecules, we have 1 hydrogen. We're looking at this formula right here. We have 1 nitrogen and we have 3 oxygens, and that gives us 1 molecule of that compound. The atomic mass is 1 times 1.01, which equals 1.01. It says rounded, but we don't do rounded anymore, so I'm going to scratch that. If you did it rounded already, you're fine. And then this one is 1 times 12.01 is 12.01. And finally, we have 3 times 16, which equals 48.00. All right, now you don't add these 3 to get this. It's basically a tricycle. You need 1 set of handlebars, 1 seat, and 3 wheels to make 1 tricycle. but these are the masses of each of these constituent elements, and so we do add them together. And so we got, what, 48, 58, 60.01, 61.01, 61.02. That's atomic mass units. And remember what an atomic mass unit is. It's essentially the mass of a single proton or a single neutron. Since we consider electrons to have no mass at all, that means it's the mass of a single molecule of this compound. All right. Now, the number of moles, all this means is, number of moles, is we take the number of molecules and we come over here and we multiply this number here by 6.022 times 10 to the 23rd. And that gives us the number of moles. It's just a basket of molecules. Okay, we could have picked any size basket we wanted, but there's a particular size basket we chose. That was chosen, and that's times 10 to the 23rd. So if we take that and multiply it by a mole, that's 1 mole, we have 1 mole. If we take this and multiply it by a mole, we have 1 mole. If we take this and multiply it by a mole, we have 3 moles. Okay, and if we take this and multiply it by a mole, we have 1 mole. So all it is taking a basket that holds 6.022 times 10 to the 23rd molecules, and then saying how many baskets do we have? We have 1 basket of this many molecules, this 1 basket of this many, 3 baskets of this many for this compound, and so on. Okay, that's not why this number is special. Why this number is special is the next column, is that it absolutely equates, these are all in atomic mass units, the mass of a single proton or neutron. But what this number does, it's the only number in the whole universe that'll do this. It equates this number in AMU to the same number in grams. And grams is what we work with in the real world. So it becomes 1.01 grams. This one is 12.01 grams. This one is 48.00 grams. And this one is 61.02 grams for a mole of these molecules. All right. The number of atoms or molecules, well, it's just this number times 6.022. I'm not going to really do the math on that. It's just 1 times 6.022 times 10 to the 23rd. That's how many hydrogen atoms that you have. This one is 1 times 6.022 times 10 to the 23rd. And I'll write it out what it is. It's hydrogen atoms. This is nitrogen atoms. And this is 3 times 6.022 times 10 to the 23rd, and that's oxygen atoms. Okay, and then this is 1 times 6 times 10 to the 23rd HNO3 molecules. Okay, so we filled out that table. So now we can answer some questions. So everything that you see in this table is based on, really we're interested more in this side than we are in this side now. It's based on making 1 mole of HNO3. That's what we've created here. So we can answer the questions based on that. So how many moles of H in 4.2 moles of HNO3? So there's 1 mole of H for every 1 mole of HNO3. So if I have 4 moles of HNO3, I'm going to need 4 moles of H. It's a 1-to-1 relationship. Okay, so it's going to be 4.2. You don't have to show work if you can do it in your head. 4.2 moles of H, but do write it out to create 4.2 moles HNO3. All right. How many grams is 2.21 moles of HNO3? So if 1 mole of HNO3 is 61.2 grams, then 2.21 moles is going to be 2.21 times 61.02. So it's 221 times 61.02 grams of HNO3. And that's going to give us 134.9. All right, how many grams of nitrogen in 0.087 grams of HNO3? Again, it gives us a chance to set up a stoichiometry equation. It's something we haven't done in a long time, and it's important that we get back into this. So it's asking how many grams of nitrogen in 0.087 grams of HNO3. So what we want to know way over here on the left, remember the way over on the left, way over on the right equations. The way over here on the left, we have grams of nitrogen. That's what it's asking us for. And what it gives us is this right here. Way over here on the left, what we start with is 0.087 grams of HNO3. Okay, now we have to build a bridge to get from here to here, grams of HNO3 to grams of nitrogen. So we got to make this cancel out. So we're going to do a molar mass conversion. So 1 mole, hopefully this comes back to you. That's the idea of going through this multiple times over months and months. 1 mole of HNO3 equals, right here, 61.02 grams of HNO3. So grams of HNO3 cancels with that and that. Now we need to go from moles of HNO3 to moles of nitrogen. So eventually want to get to grams of nitrogen, but you always have to go through moles. So it's 1 mole of, well, let's see what the relationship is. For every 1 mole of HNO3, we have 1 mole of nitrogen. So it's a 1-to-1. So 1 mole of nitrogen for every 1 mole, and we put HNO3 on the bottom because we need that to cancel. So moles HNO3, moles of HNO3. And now we need to get from moles of nitrogen to grams of nitrogen. So right there, there's the relationship right there. So times 12.01 grams of nitrogen for every 1 mole of nitrogen. Moles of nitrogen cancels. The last man standing is grams of nitrogen. Haven't heard that expression in a long time. So now you multiply the numbers. 0.087 times 12.01 divided by anything on the bottom, and that would be 61.02, and that gives you 0.017 grams of nitrogen. Okay. All righty. So we'll get to where you're proficient at those again. All right. The next one is balance the following equation. I don't want you using boxes anymore. We gotta get off the training wheels and do this the right way. But what you do want to do is count your elements, C, O, and H. On this side we have 3. On this side we have 1. On this side for hydrogen we have 6. On this side we have 2. Oxygen, on this side we have 2, and on this side we have 2 plus 1 is going to be 3. Stay away from oxygen for 2 reasons. One is it has a pure element. Stay away from any pure elements, and stay away from any elements that appear more than once on the same side of the arrow. So for those 2 reasons, both, you want to stay away from oxygen. So you can either balance carbon or hydrogen. Doesn't matter which one. So we'll go ahead and balance hydrogen first. So there's 2 on this side, there's 6 on this side, so we multiply by 3. And that gives us 3 times 2 is 6 hydrogens. That's all good. And now carbon, that didn't do anything for the carbon since we didn't change either of these. So carbon we need to get from 1 to 3. So there's 1, there's 3. So we put a 3 there. Okay, so we have 3 carbons, we have 6 hydrogens, that's all good. Now what do we need for oxygens? We have 3 times 2 is 6, and 3 times 1 is 3. 6 plus 3 is 9. It's an odd number. So we have to say, what do you multiply 2 by to get 9? We need 9. And the answer is simply, hopefully this is not so quirky as it seemed the first time we did it. It's 9 halves. So your coefficients, you didn't have to change the coefficient in front of propane there. So it's 1, 9 halves, 3, and 3. There are certain types of calculations in chemistry where you can leave the coefficient like that, but generally you don't. So what you do to iron out this fraction is you simply multiply everything by 2. So your final equation would be 2, multiply everything here by 2. 2C3H8 plus 9O2 gives you 6CO2 plus 6H2O. Okay, and there you go. That's your final answer for that. Okay, so this one says for each of the following chemical equations, really just one that I'm going to give you, do the following, list the molar mass of each reactant and product. So you go ahead and put the molar masses in there. I'm going to pause for a second and calculate those, but let's just do the first one together. Let's do H2S. So we've done this before. So H2 is 2 times 1.01 for hydrogen. And 1 sulfur. Sulfur is 32.07. That's going to give you 34.09. So I'm going to put that right here, 34.09 grams per mole, per 1 mole. Okay, the coefficients come into play when you're doing your calculations later on. The subscripts are important though. You do factor those in. So this number would include 2 hydrogen atoms and 1 sulfur atom. All right, so there's the molar masses. So now we can go ahead and compute these. So how many moles of H2S are required to produce 3.5 moles of Ag2S? So what it's asking us way over here on the right is moles of H2S. When you're starting with 3.5 moles and go way over to the right because you don't always know how much space you're going to need, 3.5 moles of Ag2S. All right, well, if you remember way back, moles to moles is just a single conversion. Okay, and we need to simply come up here and find Ag2S and find H2S, and we see that there's 1 mole of H2S for every 1 mole of Ag2S. So that's going to be our ratio. And we want to put the 1 on the bottom, Ag2S, it's going to make this cancel out. So it's simply going to be times 1 mole of H2S for every 1 mole of Ag2S. And it's just a 1-to-1, so that means it's 3.5 times 1 over 1. This cancels out. And that's going to give you 3.5 moles of H2S. Okay, let's move on. how many grams of silver will be produced by 4.7 grams of H2? Okay, grams to grams is going to be 3 conversions if you remember way back when. What we're looking for is grams of silver. So way over here on the right, it's grams of Ag. And way over on the left, give yourself a lot of space. You're going to need 3 conversions. It's going to be 4.67 grams of H2. Okay, so if you don't remember this, find where grams of H2 is. Here's H2, and here's grams down here. That's in our world. We work in the world of grams. We measure things on scales. So if we just lightly write 4.67 there, and where do we want to get? We want to get to grams of Ag over here, right there. So we have to go up into the equation, so it's grams to moles. Then we have to go across the equation, moles to moles. That's the second conversion. And then we have to come out of the equation, moles to grams, to get us to that question mark. So it's 3 conversions. So let's go ahead and do the first one here. Again, you want to get to where you're doing these in the spring without this scaffolding, without this kind of, these are kind of the training wheels. You want to get to where these problems are a little more intuitive for you and you can see how they work. But for right now, go ahead and use this if this is helpful. Okay, so it's times, we got to go from grams to moles of H2. So it's 1 mole of H2. And it's not because that's 1. It's simply because this is 1 mole of H2 is 2.02. The 1.01 for hydrogen, and you got 2 of them in a molecule, so it's 2.02. So it's 1 mole of H2 for every 2.02 grams of H2. Okay, so right away those cancel. Now you have to go from moles to moles over here, and you see there's 1 mole of H2 for every 2 moles of silver. This is where the coefficients come in, is when you're doing this calculation. So it's 2 moles of silver for every 1 mole of H2. Okay, so now the moles of H2 cancels right there. And finally, we need to get from moles of silver down to grams of silver. So it's going to be, need to use the molar mass. So it's 107.87 grams of Ag for every 1 mole. Again, anytime we're doing a molar mass, it's always 1 mole of Ag. And moles of Ag cancels. The last man standing is grams of Ag. So now you're ready to do the math. So multiply everything on the top. 4.67 times 1 times 2 times 107.87. And now you can divide by everything on the bottom. Divided by 1, divided by 1, divided by 2.02. And that equals 498.8 grams of Ag. Okay, we keep going here. How many moles of H2 can be produced? It should be produced from 6.52 grams of Ag. So we're looking over here on the right. What are we looking for? Moles of H2. And what we're given way over here on the left is going to be 6.52 grams of Ag. Okay, and so what does that mean? Let's erase what we wrote earlier and use this if it's helpful. You don't have to. So we're starting with grams of silver right here. So, and that's going to be 6.52. And what we're trying to get to is moles of H2 up here. So you have to go from grams of Ag to moles of Ag, and then from moles of Ag to moles of H2. So we've got 1 mole of Ag for every, we're using the molar mass conversion, 107.87 grams of Ag. And then we got to go moles to moles. So we've got 1 mole of H2. We want moles of H2 in the end, so that's going to be on the top of our last conversion, over 2 moles of Ag. Use that number for Ag, use that number for H2. Okay, so we go ahead and again multiply everything on the top, 6.52 times 1 times 1, divided by everything on the bottom, divided by 2, divided by 107.87, and that's going to give you 0.0, we'll just leave it there, 0.03. Okay, all right. And finally, how many grams of H2? How many grams of H2 will be produced by 5.67 moles of Ag? So we want to know how many grams of H2, so that's down here, right there. It's H2 and it's grams, and you're starting with 5.67 moles of Ag, so that's up here. So you're starting there, 5.67 moles of Ag. You got to go moles to moles of H2, and then moles of H2 out to grams of H2. So there's 2 conversions there. Okay, so we're going from moles of Ag to moles of H2, so that's a 2 to 1. There's 1 mole of H2 for every 2 moles of Ag. And then you're going from moles of H2 out using the molar mass. So it's 1 mole on the bottom of H2. We need moles of H2 to cancel, and on top is the grams. 2.02 grams of H2. Cancel, 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 cancel. Last man standing. And calculate. So it's going to be 5.67 times 2.02 divided by 1 divided by 2. And that gives you 5.73. I'm ignoring significant figures as we have and we will until right before the test. We'll start nailing that down a little bit more. Okay, so there you go. That's pages 1 through 4. I'm going to wrap this video. It's at about 40, almost 50 minutes. I'll put it up on the same module as the assignment, and I'll be doing these assignments on and off over the next 2 days, December 24th and 25th. So you'll get them little by little. They should all be done by the end of Christmas Day on the 25th. Okay, so we'll see you on the next video.